everybody. Today we are going to take another class of physics. This lesson is for grade 11, and this for week 6. This class or this presentation is delivered to you by me, Mr. Khalid. Today we are going to discuss another new topic. We have discussed a little bit about it in previous chapters, which is an electrical resistance. So please open your book on page 190 and try to follow me on those slides and on your book in parallel, please. So what's an electrical resistance? Actually, if you are going to use a short length of wire to connect a positive and negative terminal of a cell, as we can see in this figure here, this cell, it could be a cell, it could be a power supply, it could be a battery, it could be anything to deliver or to push current to move through the circuit. If we are going to use a short length of a wire like this here, short length of a wire to connect positive and negative terminal of cell or battery together. This is a minus part and this is the positive one. So as we said before, current is moving from where? Starting from positive part and then until reach the minus 1, and still continue from positive to minus. So the direction of current is like this. So if you use a short length of wire to connect the positive and negative terminal of a cell or battery or power supply together, so it causes a lot of damage to the circuit. Why? If you are going to use a short wire here, the circuit will be damaged. Why? Because the wire here, the wire in the circuit, actually not the wire, both of them, the wire and the cell, the wire and the cell may both get hot, so the temperature of it is high. Why? Because there is a large value of current to flow through the circuit, and the circuit is very short. The amount of current is high and the circuit is very short, and the resistance is very low. Because the wire is very short, the resistance is very low. So the wire and battery or cell, both of them get hot. So there is here, as we said, because there is a very little electrical resistance, is very low because the wire is very short in the circuit. So the current at the same time, and the current is large. So the current is large, resistance is very low or very little value of resistance. That's why the wire get hot and the circuit may get a lot of damage. So what steps can we do, or things can we do to make the circuit safe, or to cancel this situation here? Since the current flow in the circuit, as we said, from start from positive to the minus 1 and grow to the current going to flow through the circuit from this part until reach where? The minus 1, from positive to the minus 1. So the circuit here will get the circuit here or the current in the circuit can be controlled by adding some component with electrical resistance to the circuit, or make the wire bit longer. So the conclusion is the greater the resistance, the smaller the current. The greater the resistance, if the resistance is high, so the current will be low, and smaller current that will flow in the circuit. As we can see here in this figure, 18.8 shows a circuit which with a cell here or power supply pushes what? Pushes current through a resistor. This is what? A resistor here. So the cell here going to push the current through where? Through the circuit. Actually the cell provides what? Voltage needed to push current through the resistor. So electrical resistance is very important and always in close relation or in strong relation with what? With voltage and current. Voltage and current. Three of them are very related to each other. Okay. Actually, as we said before, there is a special name of the voltage here, or the source of the voltage to push current to flow through the circuit. As we said before, the special name is what? BD. BD cross where? Here, cross the cell or the power supply or any source of voltage. So it's called what? EMF. As we said last lesson, we mentioned it. We said it's what? It's called EMF. So this is what stands for what? Electromotive what? Force. Electromotive force. And this one actually is not a force. It's not a force. It's what? It's a voltage. It's a voltage. It's not a force. So any component that pushes current around the circuit is said to have what? EMF. EMF. This source of voltage, any source of voltage to push current, to start push the current through the circuit, it has what? Or any one of them have what? An EMF. Even cell, the source of voltage, cells, whatever, cells, batteries, power supply, dynamos, and so on, whatever. So each of them have what? EMF. EMF is what? Voltage. Is voltage. So it's not a force. It's what? A value of voltage. So what we will have here? We have three important things in each circuit. The source of voltage, which we mentioned in last lesson, V, and what? As we said, current start move from positive to minus, so we will have what? In this direction we have what? I. Okay, so since we have a power supply or a source of voltage, current start moving through the circuit. Even the circuit has a resistor, has diode, has any component here. So the current start moving. So what have here? Since current start moving, already we have what? R. So what's the relation between three of them? As we said before, V is equal what? I times R, which known as what? Ohm's law. This is Ohm's law. So this is the conclusion of what's the relation between resistance, voltage, and current in any circuit. As we mentioned it before, we can use a meter to measure what? Current, and we can use voltmeter to measure what? The voltage, the value of voltage on this resistance. Because since there is R here, R will go through this resistance R, so the voltage V is equal to the value of I times what? R. Value of I times of R, it gives what? V. V over what? The resistor here. So this is the relation between three of them. Okay. So now we will move to what? The definition of what? Resistance. What's the definition of resistance? This is on page 191. So the resistance, it's what? How much current can a cell push through what? A resistor. This is the definition. It's very easy. how much current can a cell push through a resistor. Since we have cell or power supply or any source of voltage, this source of voltage is gonna to push what? Current through what? Resistor. So how much the current can cell or source of voltage push through this through R? Actually, this depends on what? The resistance, the value of the resistor. So the greater its resistance, if the resistance is high, so the current will be what? Small. The smaller the current that will flow through it. It's the relation between I and R is the greater the resistance, or the greater is resistance, so the smaller is what? I that will flow through it. So the resistance of component, as we said, is measured with, by value of what? Of ohms. That's why it's known as Ohm's law. R is equal to what? V over I. V is equal to I times R. So the value of R, the resistance, which is measured in ohm, is equal to what? The voltage BD over I. BD or voltage V, they are the same, over what? Current. So R is equal to V over I, which is exactly answering this question: how much current can cell push through a resistor? Now we will take this example for more explanation. Work with example 2. I think it's on the same page, 191. What we have here, we have a resistor. With what? Allows a current of 0.02 ampere to flow through it when there is a PD or voltage. PD is a voltage of what? 10 V between its ends. So there is 10 V between what? The ends of this resistor. So what's the what is its resistance? What is its resistance? What we have here, we have like a resistance like this. This is R. Some draw it like this, and some can draw like this. They are same. Yes, but this is for more famous. So we have a resistance R. This resistor R allows a current of what? 0. So the current which are going to flow through this resistor is equal to what? 0.02 ampere. And the voltage between 2 points here, 2 ends of R, is equal to what? 10 voltage. 10 voltage. So what's the value of R? As we said before, R is what? First, write down what do you call the formula, or what you have in the example here. Write down what you know and what you want to know. So what we have here, we have I and V. We need to find what? R. We have I is 0.02 ampere, and V is equal to the voltage. We need to find what? R. So just substitute the values in the formula here. Like in step 2, write down the equation of R. So R is equal V over I, and V is equal, substitute the value of V is 10. Value of I is 0.02A. So divide 10 over this value is equal to what? 500 ohm. 500 ohm. So the resistance of this resistor is equal to what? 500 ohm. Here. So we have a resistance here, the value is unknown. We have a current, the value of current, we have the value of V, so we can find R. Sometimes we have R and I, we can find what? V. Sometimes we have R and V, then we can find the value of I. So next, now we are going to discuss what is an ohm. Ohm, the value of the resistance, or the how we can measure the value of resistance ohm. So now let us think about this equation here. R is equal to what? V over I. Now we are going to discuss what's the relation between the value of V and the value of I and R. So this is what is an ohm. To answer this equation, we need to study the relation, or this equation, the relation between V, I and R. This equation defines what we mean by resistance. This equation describes what we mean by resistance. So, for example, here we can say that it takes a PD. If PD is 10, here we need 10 voltage to make what? 1 ampere to flow through 10 resistor, 10 ohm resistor. This one example. Another example, it takes what? 20 volt to make 1 ampere flow through what? 20 resistors. So the value of V is in strong relation with what? The value of R and I. If V is 10 and we need 1 ampere of I, so R, it will be what? 10. If we put, or we need 20 volt, here V is 20 volt, and which or to make 1 ampere to flow through a 20 resistor, and so on. So what's the result here? The result here, or the conclusion here, is resistance in ohm tell us how many volts are needed to make what? 1 ampere flow through what? A resistor. So the conclusion from this equation is what? It tell us, this equation tell us how many ohms, or in ohm tell us how many volt here is needed, or we need for what? To make 1 ampere to flow. 1 ampere to flow through what? R. So 1 ohm, we can put it another way, or in another way, 1 ohm of R, because R is measured with ohm. So 1 ohm is what? 1 volt per what? 1 ampere. 1 ohm is equal to 1 volt to make what? 1 ampere to flow. So this equation, it can tell us about what is an ohm. We can do it in different ways. We can say that it is the amount of voltage needed to make 1 ampere go through what? A resistance. Or 1 ohm is 1 volt per 1 ampere. So this is the relation between V, R and I. Page 192, changing current. So we are going to move to another topic, changing current. What happening if current is changing out, or what things make current change? You can think of electric circuit as an obstacle race. Electrical circuit, now we can think about it as what? As an obstacle race. How? The current flow through the circuit, or flow of charge, comes out from where? From positive, as we said before, from like this. This is the positive part, and this is the minus one. So current comes out from positive terminal of the cell or the battery and must travel around the circuit to the negative terminal. Along the way, it must pass through the different components. The greater their resistance, the harder it will be what for the charge to flow, and so current will be smaller. So what's the conclusion here? The greater is the resistance in the circuit, the smaller the current that flows. This one conclusion. The greater the resistance, so if R is high, so the current is low. If the resistance is low, so current is high. However, we can make a bigger current flow by what? Increasing BD. If we are going to increase the fault or voltage, which makes current to flow through the circuit, that pushes it, so a bigger BD or voltage V, if V is high, produce what? Bigger current. So the value of B is high. So the second conclusion here is what? The greater V or BD in circuit, the greater current the flow, or the less V, the less I. So we have two conclusions here. What is this? Is one. This is the second two, or the second one. First one, the conclusion here for changing current, or what things are affecting the current to change or make current to change, is two things. What? V and R. V and R. First one, the greater resistance, or if the resistance is high, so the current is low or small. If the resistance is low, so the current is high. Another thing is what? V. If V is high, current is high. If V, the value of V is high, so the greater what? The current flow. If V is low, current will be low. Here in this slide, or under this topic, through thick and thin, we are gonna discuss what's the relation between the resistance or I with what? Thick and thin wire. So what's the relation between in general the shapes of wire with the resistance? So as we said before, the idea of an obstacle race can help us to think what about the resistance of wire of different shapes, different wires of different shapes, which is thin or thick. Shapes of wire in thin and thick shapes. So along with or with thin wire has more what? Resistance. Yes, if we have a wire like this and we have another one is like this, bigger than in shape, so what? R is along here more resistance than what? Short or fat one. So as we said before in previous circuit, I don't know what number of the slide, as we said before, if we put a short wire here in the circuit, so we're gonna damage the circuit because the wire is very short. If the wire here is very long, so the resistance will be less. Here resistance is high, here is low. So wires has more resistance than a short fat one. Now imagine an obstacle course that includes pipes of different size through which the runners have to pass. It's easy to get through a short pipe with a large diameter. So it's much harder when pipe is long and narrow. So what's the conclusion here? The conclusion is the longer of wire, or the longer wire, or the wire of the circuit is longer, the greater is what? Its resistance. So resistance will be high. The greater the diameter of wire, the less what is it is resistance. So there is a different relation of wire for long wire and the diameter of wire. Greater diameter is less what resistance. Longer wire is greater resistance, its resistance is high. So this is the relation between the wire and thick and thin. For more explanation, now try to focus on this figure here. This is a circuit. We have a resistor here. We have an ammeter, voltmeter, and what variable power supply. It's not constant one. It's variable of power supply. Here, as we can see in this circuit, the cell or power supply is changeable. We can change what the value of V, as we can see here later in this table. So we can put V2, 4, 6, 8, 10, and 12. And then we are going to say what's the value of I and the value of R. As we said before, because the current start moving from positive to the minus, so the current flow is like this, in this direction. So this is the current flow. This is the direction of current flow. So if we can here in this circuit, because the power supply and the resistor are connected in parallel, so we can put a meter anywhere here, 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 here. It's same because the I is same. And we can measure the value of V on the resistor by voltmeter. We can put the voltmeter on the 2 points here, or the two ends, 2 points here of the resistor. So this one are adjusted to give what several different values of V. Different values of V. For each value here, we have values 2, 4, as we said, 6, 8, 10, 12. So for each value of V, we have different value of what? I and R. I and R. So the current here is measured, and the result, what? It's like shown here in this table. This column is V, this column is I, this one is measured by what? V is measured by voltmeter, and I is measured by ammeter. So when we have V and I, so it's easily to find what the value of R. So what we are going to do here, we are going to change the value of the power supply here. So immediately this one going to push what? Current through the circuit. If we are going to change this, so I immediately will change with V. I will change directly with V. And then the value of R is already changed with what? The value of I and V. Here in this example, or from this equation, R is equal V over I. So we can find what the value of R in each value of V. V is 2, I is 0.08, so the value of R is 25 ohm. For example, if we put V is 6, so the value of I is 0.24, and the value of R is 25 as well. For example, if we take V is 10, the value of I is 0.4, and the value of R is what? Is 25. At the end, to find the value of R, we are going to have what? Calculate what? The average, or these can be averaged to find the value of R. So what we have here, we have a power supply here. Is it changeable or adjusted? We put different values of V, and then we are going to use the ammeter to measure the value of I. and the value, we put voltmeter to measure the value of phi. Then we will find the value of R from this equation. R is equal V over I. At the end, we will take what? The average value. Okay, sorry. Now we will move to another topic. This topic is electricity and energy. Now we will put another thing here. What's the relation between electricity and energy? This topic is on page 193. As we mentioned before, we use, or we can use, electricity because it's what good way of transferring energy from place to place. So electricity transferring what? Energy from place to place. From, for example, electricity are transferred from the station of or generation, or what do you call it, the place where electricity are generated. So then we are going to transfer it to different distances, to different cities in different places. So in most places, if you switch on electric heater, okay, so you are getting what? The benefit of energy, okay, related or released as a fuel is burned in power station, which may which maybe it's over 100 kilometers away. So as we said before, electricity is what? Alternating current. It's an alternating current, which is known as AC. AC what? Current. AC current. So why do we use high voltage for our mains supply? The reason is that supply with a high EMF or V gives what? Lot of energy to change that it pushes around the circuit. For example, as we said before in last class, I think, or last presentation, if we have 230 volt supply, it gives what? 230 joule of energy to what? To each column of a charge that travels around the circuit. So what's the conclusion here? The conclusion is the greater the value of EMF or V of a supply, the greater the energy it supplies. To where? To the charges it drives around the circuit. So the greater V or EMF of supply, the greater the energy it supplies. So there is a strong relation between what? Electricity and energy. The greater V is the greater what? Energy, as we said here. Okay. Electrical power, this is another topic here, is electrical power. It in page 194. Most electrical appliances have what? A label that shows their power rating. For each one we have a label like this. It describes what? The power rating. So here, like in this one, we have what? Microwave input power is 1550 watt. Microwave energy output is 950 watt. So the source of this one is 23 volt, which is 50 hertz. As we said here, most electrical appliances have a label that shows their power rating. For example, or an example is shown in figure 11. So the power rating indicating in watts or kilowatts, it's same. By watt or kilowatt is same. So the power rating of an appliance shows the rate of which at which it transforms energy. It shows what? It shows the rate at which it transforms energy. Now the power is what? The power is the rate at the power is the definition of power is the rate at which energy is transferred from place to place. So this is the power. It's the rate at which energy is transferred from place to place or transformed from one form to another. So the equation of the power here, the power measured in watt is equal to what? Energy transformed, which measured by joule, over time taken in what? In second. So power is equal to energy transformed on time taken. P is equal to delta E over T. Also, this equation reminds us of the definition of unit of power, which what? The watt. The watt. So 1 watt is 1 watt joule, because this one is energy. 1 watt here is equal to 1 joule over what? 1 second. It's in 1 second. Now we will say what's the relation between voltage and energy. Voltage and energy. So as we said, we have seen that EMF or voltage of supply tells us about how much energy is transferred to charges flowing around the circuit. So it shows what's the amount or about how much energy or what's the value of energy transferred to charges flowing what around the circuit. So it was what? The greater the current flowing around the circuit. So what will happen if the greater the current flowing around the circuit? So the faster that energy is transferred. The faster that energy is transferred. It's very important to keep this in mind. So, or what's the result here? The rate at which energy is transferred in the circuit or the power P depends on what? Both EMF or V of the supply and what? The current I. So the rate of energy, it depends directly on what? V and I that push around where the circuit. So the conclusion is that the final result is the following equation shows how to calculate the power. As we said from here, the greater the current flowing around the circuit, the faster that energy is transferred. So the rate at which energy is transferred in the circuit, the power P depends on what? The power P, it depends on I or current in ampere and V directly on both of them. B, to make B high, we need to make what? I high. So the first equation shows how to calculate the power. So the power is equal to what? B or power in watt is equal to current times V. B is equal V times I or I times V. And it's what? You remember that 1 watt is equal to 1 ampere times voltage. Watt is ampere times what? Voltage. From this equation, amperes times what? The power or watt here, the measured or the unit of measured power is equal to current A, which is an ampere. It could be A or AMB times what? V. So B is equal to V times I. Calculating energy. So energy is equal to what? Since energy transformed is equal to what? Power times time. Energy transfer is what? It's a power times time. It's very important to keep those equations in mind. Please try to memorize them. We have like from the beginning of this class up to now we have like 3 or 4 questions. So energy transformed, and they are all related to each other. Each one of them affect what? The another thing. Energy transformed is equal to what? Power times time. So we can modify the equation, the last equation, B is equal IV, to give what? Another equation for what? Energy. So energy is equal to what? Energy transformed here, energy transformed by joule, or the unit of this one for energy is equal to what? Current times V times time. So delta E is equal to what? Delta E is what? The value of energy transformed. Delta E is equal to I, current, times V, voltage, times T. This is what the final equation of calculating energy. So energy can be calculated through what? B, because B is equal I time V, and energy is equal to power times time. So power is what? I times V. So E, or energy transformed, delta E is equal to what? IV times T. We will take example here, work at example 3 on the same page. We have an electric fan runs from the 230 volt. So the current flowing through it is what? 0.4 ampere. So what we have here? We have V, a source of power supply, or the voltage which gonna push current to move, is V is equal to what? 230, and this value generate what? 0.4 ampere. 0.4 ampere to move through the circuit. At what rate is electrical energy transformed by the fan? So this is what? First question. How much energy is transformed in 1 minute? How much the value of energy transformed in 1 minute? So first step, we have to calculate the rate at which electrical energy is transformed. So this can be done by what? The power, P. So write down the equation of B. B is equal to what? V times I. V times I. So what we have here? We have the value, as we said, the value of V, the value of I, and we need to find out what, or figure out the value of B. The value of B. So as we said, B, now write down the equation of power, which involves V and I, and then substitute the values of both of them. So B is equal V times I. B is equal to 0.4 ampere, the value of I, and the value of V is 230. So the final result is 92 watts. So the value of power here is equal to 92 watts. Step 3, to calculate the energy transformed in 1 minute, So we are gonna use what? The value of, or the equation of energy. This is the equation of power. This is the equation of power. B. Please keep those in mind. B is equal to I times what? V. This is the power equation. So what's the energy equation? Energy equation is equal to what? Delta E. Delta E energy is equal to what? B times what? Time. Times time. So what's the final result here? Substitute the value of B here. So energy is equal to what? I times V times time, T, in 1 minute. So delta V is equal to what? We have the value of I times V. I times V, which is the power, is equal to 92 watt. So we have the value of 92 watt times what? 1 minute, which is 160 second. 60 seconds. So the energy here needed here is what? 5520 joule. So the fan's power is 92 watt, and the transformer and it transforms what? 5520 J of energy each minute. This is all for today. Please try to keep equations. It's very important to memorize all equations we have discussed today. And if you have any questions, I am happy to answer any question for you. Thanks again.